All right. So let us start today's discussion. So we'll go through a few more concepts. We'll start from where we left last time and go through a few more concepts in parallel computing. And the idea is then to look at it in action with Python, which unfortunately doesn't give you very good way of doing parallelization every way. And we'll see that. I mean, unfortunately, it's difficult to demonstrate through Python, but we'll see it in action. So let's start. So we are talking about method of parallelization. So let's start it from there. So the first topic is the method of parallelization. And so to do this, let us start with an example. The example is that say I am given the given some data. So the data can be like, for example, the number of students, the height of the number of students. So it's a data. Data is the height of the number of students in all colleges in India. So you can imagine that it's a huge data set. Okay. So you have the college name and whatever. So the college name dot dat, and in that you have the height of individual students written in there. Okay, that's just an artificial example, but anyway, so you can use that to for this understanding purpose. And what is the problem? The problem is to calculate certain statistics. So for example, mean, median, standard deviation, skewness, etc. So these are some statistical measures. So you don't really need to know what they are. Two of them you should know, but the others, if you do not know, that's all right. But it's basically you calculate certain statistical measure. So you calculate the mean for a given college, the standard deviation for a given college, median for a given college, etc. Okay. This is a problem that you have in hand. So this is, we'll see that how this can be done in different methods. The first method is what we said is called the bit level parallelization. What is done here is that, see, if I want to add these numbers or calculate the mean, I can calculate so mean is just adding numbers, right? So if I have, say, 6 such numbers, or say 8 such numbers, so each of these rectangles corresponds to one number. Okay. So what I can do is I can add these two together. I can add these two together, add these two together, and I drew 7 instead of 8. So add these two together. Then I add these, add these, add these, add these, add these. So I can do it this way, right? Now, if I look at a computer, so these numbers, each of these numbers may be represented with 4 bits. Okay. Each of these numbers are represented with 4 bits. So in the first round of operations, we are adding 4 bits with 4 bits here, then 4 bits with 4 bits here, and doing that 4 times. So this is some mistake here. So I have to add these two, and then add these two. It's only 3 rounds that we got. Anyway, so I'm adding these 4 bits with the other 4 bits. But my computer, so how this adding is done, so there is something called adder in a computer, so that has to be a 4-bit adder. to add four bits with 4 bit. And this adder can be just what you call an adder is just a XOR gate, which is 4 XOR gates essentially. Now, I may have in my computer a 16-bit adder, which means now these 4 operations which is there in the first line can be done together, because I can add 16 bits with another 16 bits at one go. I don't need to do it 4 times. Okay. So if this is possible, then obviously I am gaining 4 times the speed, and this entire thing is done in one clock cycle, right? So we talked about the CPU clock last time. So as the clock ticks, you can add 16 bits with another 16 bits, and then you can divide them as 4 different. So this first round of operation is done in only one clock cycle as opposed to 4 clock cycles if you want to do it 4 bit with 4 bit at the same time, one by one. So this is called the bit level parallelization because it's happening in the bits. So this has another name in terms of implementations. It has different names. So it's usually called vector parallelization. So you treat these numbers as vectors. So this is like adding 2 vectors of 4 components each. Okay. Now, for most of the modern day processors, this is done internally. So you don't need to don't need to write a code to do this. This is already done internally, given that you have given the processor the entire array. So if I have given this entire array of numbers, so you can imagine this as an array now. Like in Python, you are introduced to arrays. So it's an array with 4 elements. So if I give the entire 4 elements to the processing unit has this interpreter. The interpreter will understand that I can add this in I have 16 bits and they are giving me 4-bit elements for each array, so I can add 4 of them together. So the vector parallelization or the bit level parallelization will be done by the interpreter itself. You don't need to write a code for this. Okay. So this is the first thing. But remember that you have to give the full array. And this will come to us at the end of the discussion when we'll see it in action. The next thing is called instruction level parallelization. So what is an instruction level parallelization? Now, say here you have to calculate mean, median, standard deviation, and skewness, right? So say I have one line, one instruction is to calculate the mean, the second instruction is to calculate the median, third is to calculate the standard deviation, and the fourth is to calculate the skewness. Okay, so when I am looking at the data of one particular college, I am calculating all these 4 things for that college, right? So for college, I give you say 10,000 or maybe 1,000 students in the college. So I give you 1,000 numbers. You give me output of these 4 numbers: mean, median, standard deviation, and skewness. Okay. Now, when I look at an arithmetic logic unit, as I said that it doesn't do only one operation at a time, so it doesn't have only one such adder. It has many such adders inside. Obviously, you want to make a faster processor. So what you can do is, and again this is done by your operating system or compiler, is that instead of running this in serial, so you first run the entire data through the ALU, calculate the mean, and then again pass the data through the ALU, calculate the median. Instead of doing this, it will partition the ALU in certain way such that in one part of the arithmetic logic unit calculates the mean, the other part median, the other part standard deviation, other part skewness. Okay. Again, this is done by the operating system or the compiler mostly. So this is called the instruction level parallelization. Okay. So this, remember that again, I'm emphasizing this many times, that this is almost always done automatically. Then when you write a code, remember that the first time we looked at a code, we said that this block does this block does this block does this. So your code has different blocks, right? So those blocks are sometimes also called as task. And if one block doesn't require the other block, like I have the first block which is read data, then the second block is calculate statistics, and the third block is write. Okay. So in this particular case, I cannot calculate the statistics before the reading is done, or I cannot write before the statistics is calculated, right? So here I cannot parallelize these three things. But there can be examples where these different blocks works independently. For example, I ask you also to calculate the histogram of these heights. And that histogram, to calculate the histogram, I don't need to know the statistics. I can calculate the histogram separately, right? So what I can now do is that I can ask one of my computer, or one of the CPU, to calculate the statistics. The other CPU calculates the histogram. Okay. So this is called the task level parallelization. So you are dividing different such tasks to different directing them to different CPUs. So this is task level parallelization. Now, one thing you realize that to calculate the statistics or to calculate the histogram, it may take different time. So let me introduce to the concept of threading here. So it's an independent concept of what I am writing the otherwise. So I keep it in a different color here. So what is the threading? So threading is what a thread is like dhaga, right? So I can think of, if I pass the data through mean, median, standard deviation, and structure, I can think of this as one thread, because that is, I'm doing it serially, so that's one thread. On the other hand, if I am sending it to different parts of the ALU, then you can so in the, because I am sending it to only one ALU, I will not call it, I will not break the thread. The data, the calculations will be done inside the ALU. But here, for example, I am sending the ALU 1 and ALU 2. I am sending the instructions to ALU 1 and ALU 2 on also the data. The data goes in the both places of also. So here I can consider, I can think, imagine a case that this is my reading thread. Well, the reading the thread is one, and then the thread breaks into two. So one is I'm calculating the statistics, in the other thread I am calculating the histogram, and then they give separate outputs. So histogram may plot, and this may write, right? So I will have a plot here. So I'm breaking the thread into two. So these two threads can run in two different ALUs or processing units. Now these two can take two different times to be executed, which means when I try to run the next data set, I have to wait for both of them to finish. Otherwise, there can be a problem. So there is a question now of synchronization, that I have to wait my task, the next level of the data has to wait until I finish both these to write. So then you have to tell by hand that one you have to synchronize. So this is achieved, the task level parallelization is achieved. You have to write some part of code to do this. So those are called directives. in the coding language. So you have to write a directive which tells you that parallelize this task. Okay. And then there can be, so for example, you can, the simplest way of doing a task level parallelization is to parallelize a for loop. So remember that if I go to the next page, just for this discussion, so if I have a for loop which is running, say, I to the integer index is running from 1 to n, or 0 to n minus 1, doesn't matter. And then, so maybe just I'm writing a very simple example. So a I is equals to xii plus yii. So you're just adding two numbers. Now what you can do is that you can consider these as separate tasks, and then you can send these separate tasks to different CPUs. So you can write a directive here which says that use, say, 4 CPUs. So what it will do is that every 4 numbers will go to 4 different CPUs. The addition will be done in those CPUs, and then it will continue. Okay, so that is an example of a task level parallelization, which is achieved by writing some directives by the programmer. And there is a problem of synchronization. Here also there will be a problem of synchronization, because it's obvious that mean can be calculated faster than median standard deviation, or skewness. So that calculating skewness. So mean will be calculated faster, but then you have to wait until the slowest process ends. Okay. So in these two cases, the slowest process determines the speed of the calculation. Any questions so far? The best way to parallelize, or obviously it is not possible always, but the fastest gain that you can get is when we can do data parallelization. Okay. So what is data parallelization? It's simple. In this example, imagine that you have say 32 CPUs to work with. What you can do is that for each CPU, you can just send one college, data of one college. Okay. And then that CPU works all the exact same steps, goes through all the exact same instructions for that college. So it's almost like each CPU is taking a part of the data and running it completely on its own. Okay. So in this case, the original data is divided into different CPUs, and each CPU runs it separately. Processing units. Okay. In many of the cases, like let me give you an example. Remember that we calculated the case of a random walk, and then we had to do for each number of steps we had to do several realizations. We said that we have to calculate an average. For that we have to calculate simulate the random walk problem for some 124 realizations. Now each of these realizations are completely independent to each other, so I can just send it to different CPUs and do the calculation. Okay. Or the other example I have given you here already. Okay, so these are different methods of parallelization. So if you have any question, we will address it here. Otherwise, we will proceed.
So can you just once again tell data parallelization?
See, data parallelization is that, see, until now, we were working if you look at different CPUs, the way the parallelizations are done from 1 to 3, you are working, the different things are working on the same data, right? You're calculating the mean, median, standard deviation, a histogram of the same data. But now I say that, well, what I will do is that I will not bother about parallelizing mean, median, standard deviation, anything. They will all run serially, but I will send the data of different colleges to different CPUs. Okay.
Okay,
So,
okay.
so
Yes,
that's
sir.
data parallelization. Now, obviously, you can do hybrid. So you can send different to different CPUs, and then each CPU can then do the instruction and task level parallelizations, etc. So that is what one does in practice. And for that, I need to discuss something more now. So, which is how these things are achieved in. Yeah, go ahead.
So, sir, when we say CPU, so what do we mean? Like
Right.
what is the relation like core? We say you had told us about eight core, like
Right. So
octa-core.
that, so exactly that is what we need to discuss now. So what is the architecture of an hardware? Okay.
Okay.
So that brings us to this question, that what is hardware? How are these CPUs or processing units are distributed? Okay. So to see this, let me. So remember that we talked about the processing units, right? So let's assume that this is one processing unit, and then if I can copy it, and this is another one. Nowadays, you know that there were at some point Intel went to the dual core processors, and nowadays one processor has several processing units. So this is processing unit, this is another processing unit. Okay. Now one processor, I said, will have different processing units, and remember that each processor has to talk to a memory location, right? So each processor then, each processing unit then need to have a memory location. So let me draw it here and then duplicate. Right. So the processing unit which talks to the direct memory location is usually called the L1 cache. This is the fastest of the memories. Fastest means if you want to read or write to this memory, it will take less amount of time. And then these two has to be fed by some type of thing which will determine that where how much data, how much processing will be done. So that is done by, and for that, see, when you are, this entire thing is one physical CPU. This is what I now call a CPU, and this is bad. Okay, now I don't know how to. I know what to do. This entire thing is called a CPU. This is what you see from outside. I say that I have a dual core CPU, which means I have these two processing cores. So these are also called cores. Okay. So when I send something from outside, it goes to this thing called L2 cache. Okay, it goes to this memory. Just think of these as memory. And then this entire thing is connected to what you call the RAM. And the RAM is much bigger. So these are fastest. These are faster, but this is much smaller. So it can be 1 MB. This can be a little bit bigger, say 32 MB. I really do not know the size of the present day machines, but just giving you some. The RAM is much bigger, and it's also much slower than the caches. So what is happening? So remember that your instructions are, and the data is in RAM, so it's going to the L2 cache. And then depending on what type of parallelizations you are doing, so for example, you are doing the L2 cache, the processor itself can do an instruction level parallelization. So depending on that, it is sending different tasks to the different processing units. Inside the processing unit, also some instruction level parallelization can be done, and obviously bit level parallelizations can be done. But this entire system itself does not do any task parallelization, which you have to write. Okay. Now, this RAM, obviously, if you when I say that I give you the data of all the colleges, so that is not written in the RAM, that is written in your ROM, which is or hard disk. Okay, which I draw a little bit bigger. You'll see why. So this is my hard disk, and the hard disk is the slowest, obviously. Though nowadays there are very fast SSDs which are as fast as a RAM, but mostly this is the slowest one. And sometimes what happens is that you have to load so many data into the RAM, you end up eating up the all RAM space. So then in the space of in the hard disk itself, you have something called a swap or paging memory in Windows, which is so basically the hard disk is kind of used as a RAM, and as because the hard disk is slowest, so your computer becomes slow. And this is quite common in Windows because it handles this entire processing very, very inefficiently. So let me remove this because so this now I have a computer, which is most of the computers that we have, is a computer which has a hard disk, a RAM, and a CPU. So this entire thing is my CPU. Okay. So you can see if I even if I don't give it any task parallelization, this will still do the bit level and the instruction level parallelization. Nowadays it will do by itself. And then instead of 2 cores, you have at least 4 cores in most of the CPUs now. So it is quite a bit of parallelization automatically being done. And then you instead of only L1 and L2, you also have L3 cache, etc. So those are all details. But when I go to a real good computer, a workstation, now this will be replicated. So I will have more than one CPU in the workstation, usually 2 to 4 CPUs. Is another CPU, and then there is a RAM to cater to the CPU. And then this RAM also can access, obviously can read from the hard disk. And then there is a connection between these two RAMs in case you want to transfer the data from one to the other. So these two CPUs, and you can have more than two, as I said. This entire thing lives in a motherboard, and this full thing is usually called a node. And in a real parallel computer, you will have several of these nodes. So node 1, node 2, node 3, node 4, etc. Okay. And they will be connected through a network. So there is a network through which these nodes are connected. Okay. This is the grossly the architecture of a computer that you use today. There are more complications. So like for example, you can have more than one connections, one for data, one for instruction. You can have more than one network connections, one for data, one for instruction. You can have GPUs, graphics processing unit, working with the CPUs. So those details we cannot go through, but this is the basic thing. So what I request you is that our institute houses this supercomputer called Param Shivai, and there is a website of this attached to the institute website. So please go through it and try to understand, try to see that how many nodes are there, in each node how many CPUs are there, etc. Okay. A few things you can realize here is that this RAM, for example, of one node is not directly connected to the node 2. To communicate between this RAM and the node 2, you have to go through the network, right? On the other hand, this RAM is directly connected to the first CPU. So to communicate with the CPU, you don't need to go through any network. It's direct, there is a direct connection. So when such a direct connection between the RAM and the CPU exists, the RAM can be used parallelly by the CPU. Means that different cores can access different parts of the RAM. So that's called symmetric multiprocessing. I will tell you why symmetric. This is because if you ask the question how much time CPU the core 1 requires compared to core 2 to access the RAM, then the time is same. But if this core wants to access the RAM here, it will definitely take more time because it has to go through a longer path. And if it wants to access the RAM in node 3, obviously it will take much more time. Okay, so you will see that this thing many times it is written SMP. So this is what it means. This is this symmetric what the symmetric multiprocessing means. Now, if I look at this structure, we'll see that I have two cores per CPU. I have two CPUs per node, and I have 4 nodes. So if somebody asks me that what is the number of cores in your CPU, sorry, in your system, so I will say 16 cores. So this is a 16 core machine. So that's what you often hear. Now I can have, so usually then you ask the question, because this RAM is symmetrically available only to 2 cores. So if I have a 4 GB RAM here, then the other parameter which is important is RAM per core, which is 2 here. And you may also need to know what is the total RAM. How much is the total RAM for this system if each of these RAM modules are 4 GB? 64 GB, right? Okay, so this is all about the structure, and then we'll see what are the why we came to the discussion of the structure shortly. Any question, please raise.
Sir, can you explain it about the total number of RAM?
Total RAM. Okay, so this module is 4 GB, right? Here in the node, in this node, I have 2 of 4 GBs. So I have 448 GB, right? And then I have 4 of them. So I forgot this 2 here. So this is 8 into 4. Oh, this is fine. Sorry. What did I do? Okay. So total RAM is, so 4 plus 4 is 8 GB in one node, and then 8 into 4, 32 GB. Sorry. Okay. I could have arrived at that by multiplying the number of cores with the number of RAM per core also. Okay. So now we realize that the memory is not distributed. So even if I have some 32 GBs of memory in this machine, it's not available. So each of the memory part is not available to all the cores, right? So when I'm trying to parallelize, when I'm trying to do now task parallelization, I have to be careful, because remember the task parallelization is what I am writing. So I have to be careful that which part of the RAM is being used by which core. So I can do it in two ways. So how I can distribute the memory in my parallelization method. Okay, in practice there are a lot of different things that one can do, but I will just discuss two main things. So one is called the shared memory. So what is this case? So different processors or different cores, say, now that we have coined that term, shares the same memory. Okay. So how can I do a task parallelization using this? Well, imagine that this is a length of the memory that you want to access. So for example, say this is the total number of height information of all the students of a given college. So I can break this into four pieces, and or rather this I have loaded the data for four colleges, and I can have a partition like this. So this is college 1, college 2, college 3, college 4. This is in my RAM, and then I send it to four different CPUs or four different cores. Because the same memory is shared between these processors, I can do this, and you can immediately see that if I have SMP, symmetric multiprocessing, this is easier to do. And then there is a way of communicating between these two RAMs also. So in general, what one can do is to share all the four cores in this node using this type of shared memory program. Okay, so this is achieved by what is called, there is a method. So remember that we have to write the directives, and this is usually achieved by OpenMP based directives. Any question here? So OpenMP parallelization is easy, and you can see that if I look at the previous page, it cannot be done across the nodes because this network is much slower. Well, there is a way of doing OpenMP across the nodes also, but it doesn't work quite as good. But mostly it is done in a given node only. If I want to do it across the nodes, for example, here also, if you have 10,000 colleges, obviously one 4 GB or 8 GB RAM will not be able to hold the data of 10,000 colleges. So you have to do it across the nodes, which means now your memory is distributed. Memory means the data in this case, but the data is loaded into the memory and then that is distributed across the nodes. Now, if I think of this, so each node has its own memory. they're all distributed at different places, and they're communicating through a network line, right? So in this case, what I have to do is that I have to say, once I have calculated for 10 colleges, I will aggregate the data and write down the mean, median, standard deviations, etc. somewhere, right? And then again, I will calculate for 10 colleges. I will go like this. So what I now need to do is to send the instructions to different nodes, that this node, you take this much amount of data and these instructions, do this work and give me back the result. And then on node 2, you get this much amount of data, this instruction, give me back the result. Okay. So I have to distribute the memory, and then I have to communicate across the nodes to do the work. Like for when we are doing shared memory, all the nodes are doing the same task. Here also all the nodes can do the same task, but you have to tell them separately. Here, remember that this entire thing is residing in the same CPU. So L2 can decide amongst the instruction level parallelization or the bit level parallelization. Here, you cannot do that because they are completely different computers now, or completely different nodes. So that's the distributed memory computation, and you need to pass the messages between the nodes. So this is handled by MPI, or message passing interface. So there has to be now when there is a communication. So as we said that the communication is the slowest process. Communication means this type of communication is the slowest process. Even if you are trying to communicate between the RAM and the CPU, remember the instructions are also in the RAM. Your program is also sitting in the RAM, data is also sitting in the RAM. That has to go to the CPU, and the CPU has to do work and it's coming back. So if you are sending instructions very slowly, like if I am sending one instruction at a time and CPU does the work, I get back the result, then it may be that the instruction takes more time to go to the CPU or come back than this actual work done by the CPU. Okay. It is like you have 10,000 files to be transferred from one room to the other room. You may take one file at a time. Your load in transferring is less, and the file, what you are doing is you're picking up the file at one place and putting the file down in the other place. So that is much easier job. But then you can take 10 files at a time, and when you are putting down the 10 files, you are putting them in order. So it takes more time for the work to be done than going back and forth. Because the going back and forth is much slower, the communication is much slower, it is easier always that if you can communicate less compared to doing the actual work. So one need to figure out, so this is a name. It's called the granularity of the program. And probably will run out of time today. Okay, that's okay. So what is the meaning of granularity? So we say that time in communication and take the ratio of time in computation. Okay. So if this is much less than 1, let's say less than 1, we call it actually much less than 1. We call it a fine grain program. So much less than 1 means that I have very less computation. Sorry, this is much greater than 1 if I am reading this way. I have very less computation compared to the communication. This may be required for finite optimization. What do I mean by that? It means that, say, every time you are not doing the same job, you are doing different jobs. If you are doing different jobs, obviously you have to send the instruction more often, because the one instruction by definition does one job, right? So in that case it will be required, but then you will lose a lot of time in communication. On the other hand, if this is much less than 1, so this is called a coarse grain program, and this requires this will run much faster because the communication time is less, but you will not be able to optimize the program. So this is good for repetitive tasks. Okay, so this is all that I wanted to tell you, and we will run out of time, so I will not be able to show you the things in action. So what I will do is that I will upload a video later in the week, maybe in the weekend, which will show you some of these in action and what happens when you try to implement codes in parallel in C and Python. Okay, any questions? We have 5-6 minutes, we can go through those if you have any thing to discuss. Otherwise, I will not go through to the demonstration right now.
So your take communication is communication between the RAM and the CPU, right?
Right. So any communication. So it can be the communication between these two, I mean, the RAM and the CPU, communication between the node 1 with the node 2,
Okay, so the net communication
the
time.
net communication time. Yes.
Okay.
Okay. Can you repeat once? Vishwanath.
Sir, about the state multiple, so symmetric multiprocessing.
Okay. See, because this RAM is visible to both the processors, both the cores here, the time to access something from the RAM for the core 1 or the core 2 will be same, right? Almost same. So nowadays you can have 32 processors in one CPU. So all those 32 processors can virtually see the RAM almost similarly. I mean, it doesn't take much time for the time to get a response from the RAM for processor 1 is same as a processor 31. Okay. That's why it's called symmetric. But if you ask the question that how much, if I have some data in this ROM, okay, remember that we are talking about that example that you first. So if I go back to the first slide, so if you remember that I do this calculation in 3 steps, right? So imagine that the first step is done. So the first two addition is done in the first CPU, and the second two addition is done in the second CPU. Okay. So the first addition is done here, the second addition is done here, third addition is done this CPU, fourth addition is done here. Okay. So now this data comes here. So I have two numbers, right? And I have two numbers here. So this data again goes back. So one of this core calculates and then it gets one number. And the other here also it goes to these two CPUs. It calculates, it gets another number. So that is the second stage of operation. I am in the page 2, sorry. Okay. So first I have given the data for addition job to these four cores, and then the first set of additions gives me these two datas, this two white circles, and here it gives me these two white circles. So these are the added numbers. These added numbers now goes to these two cores again, and these two goes to these two cores, and then we get one added number. Now these two numbers are in two different RAMs. Now I have to bring this number here, then I have to send it to one of the core, right? So till now what was happening is symmetric multiprocessing, because the same RAM is being accessed by the same CPU. But now this processing unit want to access the RAM from the other CPU. So that will not be symmetric anymore. So now you have to wait until this comes there and then goes to that. All right. Thank you. That's it for today.